So similar problem, but different. This time we've been given, so in the first question we're given the acceleration profile. We figured out everything from that. This time we are being given the velocity profile, and we're going to try and figure everything out from that. So a particle moves in a straight line with the velocity shown below. So it's going at 2 meters per second for 10 seconds. Then we can see it's accelerating until it gets to 6 meters per second at 18 seconds. Then it's decelerating till it gets to minus 6 meters per second at 30 seconds. And then it's traveling at constant speed of minus 6 meters per second after that. And so what we want to do this time is just try and do the same thing and figure out the displacement graph and the acceleration graph. Now, just trying to think whether we want to go through all the equations. Look, I think it's worth it. We could try and do this graphically, and we'll probably check it graphically, but I think it's just worth trying to figure out what's all the equations for this graph. So let's have a look at each stage. So how many stages have we got? We've got 1 stage to here, 2 stages, 3 stages, 4 stages. So let's start at stage 1. And again, I'll do the time from the start of each stage rather than trying to keep a constant or using the same time the whole way through. So stage 1, and let's try and figure out the equations for each of the stages. So what we know for stage 1 is the velocity is constant, and so therefore we know that the acceleration at t1, so the time from the start of stage 1, is just going to be equal to 0. So we know, we can see the velocity is not changing, so therefore a is equal to 0. We know that v at any time during stage 1 is just equal to 2 meters per second. Okay, we can see that here. It's 2 meters per second for this whole time. And so therefore the distance in stage 1 is just the equation we want to use is the one for constant velocity. So it's S naught plus V naught times T. So the full equation, if it wasn't constant velocity, would be half A naught T. This is all T1. So time from the start of stage 1, T1 squared, but the acceleration is 0, so this term disappears. So therefore, in stage 1, S T1 is just equal to, so the displacement, now what does it say about the initial displacement? Minus 16 meters. Okay, so it's saying the initial displacement is minus 16 meters. And so this is starting at minus 16 plus the velocity for this stage is constant at 2 meters per second, t1. And so it's just going to be 2t1, just changing the order to make it look nicer, minus 16 is the displacement at time t1. Stage 2. I wonder if I'd been better doing this down here. Maybe so, just so I can get all the stages in a row. Okay, now you might not need to go through all this working. You might be able to figure this out as you go along. I'm just doing it in full so that people can see what's going on. But just be aware, the more working you do, the more likely it is that if you make a mistake, you'll still get some marks for this stuff because I can see that you know what you're doing, but maybe you just made a silly mistake. Whereas if you do no working, then you won't get any marks if you don't get the final answer right. In any case, when you're doing calculations in your work, you have to show what you've done so people can understand it, because other people need to understand what you've done to make sure it's correct. So where are we? We're at stage 2 now, and so we can figure out this acceleration. So it's accelerating, the velocity is increasing, so it's a positive acceleration. We're kind of working backwards here, and so we would have, the formula would be, so V, and so it's the time into stage 2. So we're resetting the time at 10 seconds, and we're just looking at the time from 10 seconds onwards. So at this point, T2 is going to be 0. So V of T2, this is just deriving it really if you needed to, is equal to your initial velocity plus acceleration your initial acceleration times T2. And in our case, what have we got? I don't know if this is the best way to do it or if it's just easier just to calculate it. But we could go through this. So once we get to 18 seconds, so that's T2 is 8 seconds into this stage, so it's at the end of this stage, then the velocity is going to be 6 meters per second. So therefore 6 is going to be equal to, the initial velocity was 2 meters per second plus acceleration times, and the T2 is 8 seconds into this stage. So therefore the acceleration is just equal to 4. So take this over, take the 2 over, you're going to get 6 minus 2 and then swap sides. So it's just going to be 4 over 8, which is equal to half meter per second. Okay, so we just figured out, and you could have figured that out. So it's changed by, and probably that would be the way to do it, it's changed by 4 meters per second and 8 seconds. Therefore, the acceleration is just equal to 4 divided by 8, which is half meter per second, or 0.5 probably would be a better way to write it. So 0.5 meters per second. And so that's going to be the acceleration at, and that's constant. So it's the same acceleration the whole way through. And so for any time in stage 2, so the acceleration at any time in stage 2 is just going to be 0.5 meters per second. Let's have a think about displacement now and see where that takes us. So at the start of stage 2, so let's just figure it out from here. So at the end of the stage, of stage 1, S of its end of stage 1 is after 10 seconds. So the displacement at 10 seconds is just equal to minus 60, so it's 2t minus 16. So it's going to be 2 times 10 minus 16, which is equal to 4 meters. So at the start of stage 2, this initial displacement at stage 2 is going to be 4 meters. So therefore, the equation for displacement is just equal to displacement at time t is equal to initial displacement plus the initial velocity times t plus a half acceleration times t squared. And the acceleration is constant, it's this 0.5 meters per second. So therefore, for stage 2, so this is st2, for stage 2, s of t2, the s at time t2 is just going to be, so the initial velocity for stage 2 is 4 meters, it's the same as the velocity at the end of stage 1. So it's going to be 4 meters plus 1/2 times t plus half a squared, so that's going to be 0.25, so half a, so a is 0.5 we figured out, so 0.25 t squared. Can't simplify that any further. What we can do though is just figure out what would the displacement be at the end of the stage. So that's the start at stage 2, it's at 4 meters. At the end of stage 2, it's going to be 8 seconds is the total length of that stage. So it's going to be displacement at 8 is going to be 4 plus 0.5 times, this is all t2. So it's all, we've reset that t to start again as soon as it comes into this stage. So 0.5 times 8 plus 0.25 times 8 squared, which is equal to 4 plus 0.25 times 64. This is going to be 24. It's going to be 24 meters at the end of stage 2. Stage 3 now. This time I won't go through the equations, we're just going to figure out what that acceleration, or in this case it's a deceleration, it's going to be negative, is going to be. So at the start of stage 3, the velocity was 6 meters per second. By the end of stage 3, it's minus 6 meters per second. So the change in velocity is minus 12 meters per second. So the acceleration is going to be the change in velocity, so minus 12 divided by the time it took, So it's gone from, it was 18 seconds at the start to 30 seconds at the end, so that's 12 seconds. And so the acceleration is equal to -1 meters per second squared. I'm just noticing that I've done that wrong. Meters per second squared, meters per second squared. Just for the accelerations. Does that make sense? We've changed negative direction 12 meters per second in 12 seconds, so that makes sense. So we've now got our A acceleration. Now we can figure out the displacement. So we'll reset T again. So T3 is the displacement from the start of stage 3. So that is going to be, we'll just use the standard formula first. So S naught plus V naught T3 plus half the acceleration for this stage times T3 squared. Now, we've already calculated down here, we calculated the initial displacement, so therefore displacement during stage 3 at the time from the start of stage 3 is just going to be equal to 24. The initial velocity was 6 meters per second. We can see that up here. The initial velocity was 6 meters per second, so it's going to be 6 times T3 plus a half times 1, but it's -1, so it's going to be minus a half times, because it's half times -1, T3 squared. So by the end of stage 3, so that's going to be a time, so it starts at 18, finishes at 30, so this whole stage is 12 seconds long. So the displacement at the end of that section, S12, is going to be 24 plus 6 times 12 minus a half times 12 squared, which is going to be 24 plus 6 times 12 minus 0.5 times 12 squared. It's 24 meters again. Interesting. So it must be going and coming back. You know, this is the displacement, so it must be getting to somewhere and then coming back again. And we have a stage 4. Can I shuffle this stuff across enough to fit it all into one line? Probably can. The stage 4 should be quite simple. Stage 4. So in this stage, you can see that the velocity is constant, so therefore our acceleration must be 0. Let's go back up here. So this is stage 4 here. So velocity staying constant at -6, so the acceleration is 0. So the acceleration is equal to 0. Then, because acceleration is 0, so we'll reset the time again to start at the beginning of stage 4, and it's just going to be equal to, so the initial displacement was 24 meters, which is, oh sorry, write out the equation first. So the equation for constant velocity is equal to the initial displacement plus the initial velocity times time, or just any velocity, it's constant velocity, the velocity at any time, so v naught times t. So that's going to be 24, and then v is -6t. 24 minus 6t, and we could just figure out the displacement at the end. Displacement at, so the end of stage 4 is after 10 seconds, so displacement 10 seconds is 24 minus 60, which would just be -44. Don't really like the look of that. What I might do, it's okay, we'll keep it for now. I'm just thinking about what we're going to end up with. Whatever, it is what it is. So -44 meters is where it's going to end up. So let's try and draw this the graphs now. The acceleration one will be easier, so let's do that first. So what we've got is acceleration is 0, then acceleration is 0.5, and then acceleration is going to be -1, and then it's back to 0 again. So the largest we've got there was 0.5 minus 1. Where's this? Just try and line these up so that if we zoom out it makes sense. So we're going to have 40 seconds altogether, wasn't it? So we're going to have 0.51, and this is acceleration in meters per second squared. And then we're going to have minus 0.5 minus 1. So what have we got here? And so then just check what I used. Yep, just 10, 20, 30, 40. And this here is the time in seconds. So it started off 0 until it gets to 10 seconds. We've got 0 acceleration. Then we've got positive 0.5 until we get to 18 seconds. So to there. A bit too far maybe. Just indicate what that is. And then it goes to -1. And it stays there until the total time gets to 30 seconds. And then it went back to being constant velocity at the end. So it's back up to 30, back up to 0, sorry. And then it continues at 0 until it gets to the end. And so this was 0.5 meters per second squared, and this was -1 meters per second squared. So that's the graph of acceleration versus time. Now this one's gonna, the displacement versus time is gonna have to be pretty big. I wonder if I can fit it in here. Probably can. Oops, probably didn't want to do that. So it is going to have to start, it's going to have to start from -44, and it's going to have to get up to at least 24. And we're going to have to figure out some intermediate points here, I think. But let's have a look at it first. So we'll try plus or minus 50, see what happens. I'll try and do it pretty close, I reckon. So that would be, so 5, 10, 10, 20, 30, 40, 50. So 10, 20, 30, 40 and 50, and this is displacement in meters. We're going to go -10, -15, minus y, don't know, -10, -20, -30, -40, -50. This way, 10, 20, 30, 40. This here is time in t in seconds. Okay, so first one's easy. This is a nice straight line, and so you can tell that because it doesn't have any square term in it, so it's going to be a nice straight line. And you could plot some intermediate points if you weren't sure about that, but it's just going to be, so it's going to start at -16, so it's going to start down here, and then it is going to, by the end at 10 seconds, it's going to be at +4 meters, so it's going to be something like that. Now let's just check that against these areas. so the velocity, so it's the area of this. And so we have got, this is 2 meters per second times 10, so it should change by 20, and that's what we're getting. So we're going minus 16, and the change is going to be the area under the velocity diagram. So it's going up by 20, so we're ending up at plus 4. So far so good. The next one, we might have to figure out some intermediate points. So what have we got? We have got S at time t, and t is the t2, so it's the time from the start of the stage. It's going to be 4 plus 0.5t plus 0.25t squared. And by the time it gets to by, why did I do 8? Oh yeah, 8 seconds in. So by the time it gets to the end of this stage, which is at 18, it's going to be at 24. So it's going to be here somewhere. Okay. Now, this time it's not going to be a straight line, because as you go along here, the area under this is increasing, the area between any 2 points under here, if you see what I mean. So if I was to divide this up into different little sections, so it's small area to start with, change is small, big area at the end, so change will be big. But let's just figure out some points. I'm just checking I've got this right. 4 is correct. 0.5 t. Where did I get that 0.5 from? Just checking that. T, because it's the initial velocity. The initial velocity is not 0.5. The initial velocity is 2. Always worth checking this stuff as you go along. So, looks like that's wrong. So that's 2. Okay, what I'll do is well, it's worth seeing it just to see. So that's going to be 2 times 8. So this here is going to be 4 plus 2 times 8 plus 0.25 times 8 squared is equal to 36. Sounds a bit more sensible. And then that's going to change this one here. So this is going to be, so let's just check we've got this one. So the velocity at the start of stage 3 should be 6. That's correct. And the acceleration during stage 3 is minus 1, so that's also okay. But that should have been 36. So it's going to be 36. So it's 36 plus 6 times 12 minus 0.5 times 12 squared, which is 36. And this one here is going to change, because this is also 36, so that's going to change too. So it's going to be 36 minus 6t. 36 minus 60, which is going to be 24, which is a little bit more sensible, 24. So we didn't need such a big graph after all. So, still interested in this bit though. Anyway, so at the end of this stage, after 8 seconds, it's going to be at 36. So it is going to be here somewhere. About here. Let me just get rid of that wrong answer. And let's just look at some intermediate points now. It should be curving up the way, this one, but let's just see where we get to. So let's just calculate at 14, say, halfway in. So that was 18, so at 14, so this would be 4 seconds. So I'll just calculate what that would be. So that's going to be 4 plus 2 times 4 plus 0.25 times 4 squared. So I'm just putting 4 into this equation here, and that's going to be 16. And so it's going to be about here. And I could calculate some intermediate points as well, but shouldn't be too bad just to draw it like that now. Maybe curving up a bit too much, but it's on the right direction. Then what? So then we've got, by the time we get to 12 seconds into stage 3, which is the end of stage 3, which is at 30, we're going to be back at 36 meters again, apparently. And so this is going to still be at 36 meters. Let's just get some intermediate points here. So for 18, I think I forgot to change that number there. So let's just try a couple of points. Let's stick 20 into here first. So 24 plus 6 times 24 minus 0.5 times 24 squared. Why did I have 24? Let me just figure out what I'm doing here. I thought I just fixed that, or did I not go through it? So I need to fix both of these. So let's try that again. So we've got 36 plus 6 times 20. Let's just try 0.20, say, minus 0.5 times 20 squared is equal to 44. So up here, now what's happening to the area here? So it's going up, but it's going up less quickly. The area is reducing as it goes along. Okay, let's just keep going. So it's going to get to 44 at 20. So it's about here at 20. Let's try 25. So I'm just going to put 25 into this. Hold on. What are we actually doing here? So what am I saying here? So this is 36. So I'm looking for what it's going to be at 20, but I've got to remember that I'm using this T3. And so T3 is the time from the start of this stage. So at 20, so at the point 20, T3 is equal to 2. So let's figure that out. So it's going to be 36 plus 6 times 2 minus 0.5 times 2 squared, which is equal to 46. So at 20, it's going to be 46. Okay, and then let's say figure it out at a time of 25 seconds. Well, this stage started at 18, so that's 7 seconds into this stage. So I'm going to put 7 into this equation now. So I'm going to get 36 plus 6 times 7 minus 0.5 times 7 squared, which is going to be 53.5. So 53.5 would be about here. Then let's try, I don't know, 20. Well, we should know 30 is equal to 36. So 30 is going to be 36, which is about here. Let's just try 28. So that would be 10 seconds into this stage. The stage started at 18, so 28 would be 10 seconds in. So I'll just substitute 10 into this. So you're going to get 36 plus 6 times 10 minus 0.5 times 10 squared, which is equal to 46. So it would be, so at 28 it's going to be about 46, which is about here. So we are going to get something like, this is coming up, and it's going to be something like this. Try and tidy that up a little bit. I just find one more actually. Let's just find, say, 22. 22 would be about there. So that would be 4 seconds in. So I'll substitute 4 seconds into this stage. So it's going to be 36 plus 6 times 4 minus 0.5 times 4 squared. It's 52. So it's going to be 52. 52 would be about here. Just trying to, it's a wee bit hard to draw this on the surface. That's the end of that stage. Now we've got zero acceleration, so we're back to constant velocity, and we know it's going to go to minus 24 meters. 36 minus 6 is minus 24, so it's going to come down to minus 24 about here. Because it's constant velocity, it must be straight line change in displacement. So it's going to come straight down like that. So we're going to get a graph something like that. Now, so that's us drawing the two graphs. We've got our acceleration graph and our displacement graph. Not terribly tidy, but let me just tidy that up a little bit. If I can, it's a wee bit better. Then the question's asking us to try and figure out, determine the total distance travelled by the particle. Determine the total distance travelled by the particle. So the displacement, this is the displacement, and so it's getting further away from the starting point. So here it's minus 20, then it goes past the reference point. This is zero displacement here. Then it's going in the positive direction, then it's coming back again. Now, to find the total distance it's travelled, we're going to have to find this maximum value here. We're going to have to find that maximum value. Now, what do we know about that? Well, we know at that point, this maximum value is just where it's turning around. And so it's heading in this direction, then it's coming back again. So we know at that point, that's where this velocity is equal to 0. And so what we can do, let's just have a think about that, what the best way to do that is. So we've got the velocity is equal to 0. And we've got these equations as well. I didn't write down my equation for velocity in this one. For these ones here. So let me just add that in, because I think we're going to need it. I didn't really worry about it because I wasn't drawing those graphs, but it's kind of asking for that. So let me move this one down. And let's just bring this out the way so I can fit my velocity in there. So it's in stage 3 that we're going to get this maximum displacement. So just to recap, what I'm doing here is we need to find the total distance it's travelled. To do this, not asking for the displacement, it's asking for the total distance. And so we're going to need to know this distance it goes out the way, and then this distance it's coming back again. And so to do that, we've got this point here, we know this point here. We should probably write those down actually. And so this here was minus 16. This here was minus 24. So what we need is, we need to know what this point here was in order to figure out how far it's gone out and how far it's come back. Now we can guesstimate it. It's probably, what was that? It looks like it's about 55 or something like that. But we better calculate it exactly to figure out what that is. And so I'm just writing down, just putting down the velocity equation. So velocity at time t3 from the start of this stage is just going to be equal to v naught plus acceleration for this stage times time, which in v naught, the velocity at the start of this stage was 2. Stage 3, isn't it? So it was 6. Was 6 meters per second, and then the acceleration was negative, so it's negative and it's negative t. So what we can do is we can figure out the time at which the velocity would be equal 0 using this equation. Then we can put that into the displacement equation and find out what the displacement was at this point where the velocity equals 0. So let's try that. So what we're doing here is for max displacement, we know that the velocity is equal to 0 because it's turning around at that point. So it's 0 meters per second. I'll give this equation a name. So let's call this 1. and let's call this, the simplified version of it is this one, 2. So sub in 1, so that means it was 1. So 6 minus t must be equal to 0. Therefore, this is t3. So it's the time into stage 3, t3. This is also t3, time into stage 3. So 6 minus t3 equals 0. So t3 is equal to 6 seconds into this stage. Does that look about right? It does. So this is probably about 24 or so. So it looks like it is about right, 26 seconds into there. And then we're going to sub t3 equals 6 and 2. Okay, so this one here to calculate the displacement. So we're going to get, let me just grab it, will be easier. So this was equation 2. So we are going to get 6 seconds into stage 3 is going to be 36 plus 6 times 6, which is also 36, minus a half times 6 squared. It's a 36's, which is equal to 36 plus 6 squared minus 0.5 times 6 squared is equal to 54. And we've probably actually calculated that before, but anyway, that's how you would figure it out. So it's 54 meters is max displacement. So let's add that to our graph. And it occurred, when did it occur? 6 meters, so it's about 24. So this here is going to be at 24 seconds. And it's going to be 24 seconds, and it's going to be 54 meters. So therefore, the total distance travelled, we've gone from minus 16 meters and all the way to 54 meters by the time it gets to 24 seconds. And then we've gone all the way from 54 to minus 24. So therefore, we can figure out total distance travelled So it's minus 16, sorry, to start with. So it's minus 16 plus, so that's from here to here. Let me kind of draw it with. So going from here to here, you've travelled 16 meters. Then you've come all the way up to here. So that's another 54 meters. So going no negatives when you're talking about distance travelled. And then we've gone from 54 back to 0. So that's another 54 meters. And then we're going to go from 54 to minus 24. In green, so I'm going from here to here. So that's another 24 meters we're going to travel, which is going to be equal to 30, 40, 40 plus 108, 148. I'll check it with a calculator in a minute. 148 meters. So 16 plus 54 plus 54 plus 24, 148. So the total distance travelled is 148 meters. Geez, it's a long question. Now, what else did I want to know? Find the times at which the particle is 36 meters from the origin. So we could have done that with these equations, just figuring out the equations, but actually we've already found that out. So it was 8 seconds into stage 2, and it was 12 seconds into stage 3. So it just so happens that we've actually calculated those already. And so we're looking for the points where the displacement was 36, so it's about here. And so these are the times down this way. So it was 8, so it was at the end of stage 2. Oh, it doesn't look like 36, sorry about that. Don't know what I'm doing there. So let me just get it right this time. So it was at 36, which is near there somewhere. It was here, and there's another one here. And that was at the end of that stage, actually, wasn't it? It's at 18. And this one is at about 30 seconds, something like that. So let's double check that. So stage 2 started at 10 seconds, and this 36 was 8. It was at the end of stage 2, and this one here was 12 seconds into stage 3, which is also at the end of stage 3. And so the points at which it was 36 seconds was 18 seconds, 36 meters per second. Hold on. The times at which it was at a displacement of 36 meters was at the end of stage 2, which is at 18 seconds, and at the end of stage 3, which is at 30 seconds. So the particle had a displacement of 36 meters at 12 seconds. Go back up and check. Sorry, 18 seconds was the end of stage 2. And 30 seconds was the end of stage 3. Well, good question. I think we're done. Hopefully it's right. I haven't really checked anything there. But let me know if I've stuffed up somewhere. Let me know and I'll fix it.